Good afternoon. Welcome to another session on masonry structures. Today we're going to talk about design of solid walls with piers under concentrated loads. Previously we have seen to design solid walls under uniformly distributed loads. We have seen hollow walls which can be designed for uniformly distributed loads. Now we're going to look into a slightly different way of designing, especially when it comes to point loads or concentrated loads. Now, the thing about point loads or concentrated loads is that when they act upon a particular point in a masonry structure, they exhibit a lot of local stresses. There is a stress that is involved that is happening all the way through the entire wall, but then there is a local bearing stress that is being acted upon that particular masonry structure. Now we need to make sure that if it is safe against any of such extra stresses that are developed due to that particular point load. So let's just quickly start with a small example. The example says that to design an exterior wall of workshop building with a height of 3.6 meters and carrying a roof truss at top with a distance of 4.5 meters from each other. So we have a model over here which has been previously made already with two external walls that are supporting a roof truss, and the spacing of these two trusses, from each other is 4.5 meter. That is, truss to truss spacing is 4.5 meters, and the height of this particular structure is 3.6 meters, which is represented over here. 3.6 meters is the height of this structure. Now this is only the height of the wall, not including the truss. So let me just hide the truss. So you can see it is 3.6 meter high wall, and furthermore we have some more cross-sectional dimensions that needs to be addressed. The width of the pier, this is a wall with piers, so we need to make sure that we should consider the stiffening coefficient as well. So the width of the pier is given as 0.4 meter or 400 mm. The thickness of the wall is 200 mm. The thickness of the pier is again 400 mm. Now this is very important. We need to make sure that we don't confuse with any of these sectional dimensions. Width of the pier, or WP, it's 400 mm, which is going parallel to the wall. Now thickness of the pier is going perpendicular to the wall, that is again 400 mm. Now thickness of the wall, TW, is 200 mm or 0.2 meter, and the width of the wall, obviously that is basically the length which is spanning from left to right over this particular view. So let's just quickly dive into the problem. Now the concentrated load is exactly acting at the center of the wall, exactly in the middle of the wall thickness, and this is where the truss is actually landing, exactly at this particular point. So the load of the point load is given at a magnitude of 30 kilonewtons acting at the center of the wall, and there is a roof load of 7 kilonewton per meter, which is nothing but the UDL, a general roof load by the virtue of the entire truss that is existing. If you can just see, if you see this truss, the truss is exhibiting a certain amount of roof load that is acting upon these two walls. Now that is 7 kilonewtons per meter. Next, moving on, we are ignoring any wind loads or seismic loads in this particular condition to make the solution much more simpler. Next, let the wall thickness be 200 mm, just like we have we have just seen those cross-sectional dimensions. 200 mm wall thickness. Pier width is 400 mm, which is this one. Pier thickness, again 400 mm, which is this one. And wall thickness, which is 200 mm, already mentioned that. Now we need to make sure that we assume a bearing area. The bearing area is a small area where you can expect the entire concentration of that point load to happen. Let's just say that it is the point where the truss will exactly be landing on, and it is going to be on a certain bearing area, and it is going to exert all that load in that little area, or in that little square which we consider as a bearing area. So the bearing area which is considered over here is 200 by 200 mm, 200 by 200 on this particular section. Let me just hide this back. Yeah. So we are considering that 200 by 200 somewhere at this particular point as the bearing area. Now, I mean, this is the point where the truss is landing, so that is why we are considering that as the bearing area, which is 200 by 200. You can consider more, you can consider less, but 200 seem to be ideal because it is complying with at least one dimension side. So, moving on, let's check for the bearing stress. Now, bearing stress is usually happened by the virtue of concentrated load, as already discussed. So, load by area is nothing but the stress developed. Load 30 kilonewtons, area 200 by 200, 200 times 200 mm square. On simply solving that, we get 0.75 Newton per mm square, which is the bearing stress developed at that particular region. Let's just simply put a rough region. So that is the amount of stress that is developed in that particular region, which is 0.75 Newton per mm square. Now, we ought to select the type of bricks we are going with, especially in terms of compressive strength. 7.5 Newton per mm square crushing strength is opted for this particular brick. The mortar grade of M1 is also opted for this particular brick. Now, if you go to table 8, if you go to table 8, you can see for an M1 grade mortar with a 7.5 Newton per mm square crushing strength, we have 0.74 Newton per mm square. This is the basic compressive stress that is generated by that particular combination. I mean, that is the that is the amount of strength that it can exhibit. So when it comes to our particular problem over here, we are talking in terms of the concentrated load. Again, we are not talking in terms of UDL. Had it been UDL, we simply multiply with whatever factors that we are considering, the stress reduction factor, the area reduction factor, or the shape modification factor in their respective tables. Table 9 is stress reduction factor, and we have other factors that we consider for UDL. But in this case, we are trying to consider, I mean, we are trying to involve concentrated loads. So there is a clause where the load, the resistance offered by this particular brick unit at this particular area is actually much more higher compared to that of the resistance or the crushing strength offered by the entire wall unit. Now that increment in strength is attributed either by due to lateral restrainment or by due to the triangular distribution of load, but then the increment is in the magnitude of 50% more to that of the basic compressive stress that is obtained from table 8. So whatever value that you're getting from table 8 for that particular choice of mortar and crushing brick type, which is 7.4 in this particular problem, we are going to multiply that with 1.5 times, or we are just going to increase that with 50% to itself in order to get the actual compressive stress offered by this particular brick unit. So 0.74 times 1.5, that will give us 1.11 Newton per mm square. That is the bearing stress, which is actually 50% more than the bearing stress you have seen in table 8. So this bearing stress is strictly limited to this, the first part of the entire wall at this point where the compressive where the concentrated load is happening. The bearing stress offered is only limited to that part. Now we ought to calculate for the rest of the wall as well. So this is these are two checks that we have to do. One is near the tip and one is for the near the bottom. So moving on, let's just simply try to compare the values which you have got. The bearing stress, I mean the allowable bearing stress is 1.11 Newton per mm square, but the actual value which we have got over here is 0.75 Newton per mm square. That is by the virtue of the concentrated load happening because of the truss at this particular point is 0.75 Newton per mm square, but the bearing stress from the code 1905 from table 8 increased by 50%, we get 1.11 Newton per mm square. That means it is well under 1.11 Newton per mm square. That means it is safe. The bearing stress that is happening over there is in a safer limits. Moving on, we need to check for the compressive stress. Now the compressive stress is more about the entire wall that is happening below that particular point. So this takes the entire cross section of the wall into consideration. So in order to know how that particular load is being distributed, yes, UDL in general, it is applied uniformly throughout the entire span of the wall. But then when it comes to concentrated loads and its application over a span, we need to make sure that it is done accurately so that we don't get any uneconomy in terms of execution. So the best way, the best approach to get through that is the trigonometrical approach, where we have the triangular effect or the arching effect, which happens by the virtue of concentrated loads that are happening on top. If you see this little diagram over here, the concentrated loads will be dispersed at an angle of 30 degrees from the particular point of action to the bottommost part of the base or the landing. So this 30-degree dispersion is seen especially when it comes to point loads in terms of the load distribution. Point number two in this particular paragraph, if you see the dispersion of load with the depth of the brickwork, uh, the dispersion of the concentrated load through the brickwork is assumed to be through an angle of 30 degrees. So we are considering that particular 30-degree angle over here. I have already made a small triangle which is making 30 degrees to its normal on both the sides. So that's 60 degrees in total. So if you try to extrapolate these lines, the triangular lines, all the way till the base, till the end over here, just extending those triangular lines all the way till end, till here. So the space or the span which is encompassed between these 2 points is what we are considering for the load that has been applied on whatever the load, concentrated load that is happening, is distributed in this particular pattern to the bottommost part of this particular line. Now to calculate this geometrically, we can simply measure the distance from this point to this point. We get it straightforward. But then if we are not having this particular setting in terms of identifying the spans, you can go for the trigonometry approach, where the triangle which is involved is making a 30-degree to its vertical, where you can take tan theta in order to find the bottommost base. So you can divide the base L into L by 2, 2 L by 2s, and you can take it as tan theta is equal to opposite by adjacent. Your opposite is L by 2, your adjacent is nothing but the height. Now the height of the triangle at this scale or at this scale is nothing but the height of that particular point from the base. So if you're taking on a full scale, the height would be 3.6 meters from top to bottom. This is the entire triangle we are taking, which is at 30 degrees dispersion. So 3.6 meters is the height, L by 2 is the base, and tan theta is equal to opposite by adjacent, that is L by 2 by h, or 3.6 meters is equal to tan theta. So on solving that, we are left with 2 times 3.6 meters tan theta. We'll be left with 4.157 meters, or in other words 4.16 meters. So if you just see this particular dimension over here, which is already made, I mean by simply extrapolating, you can see that it is 4.16 meter. This is purely done in a geometrical model which is showing you an exact 4.16 meter, and this is done on a trigonometrical approach which has a simple solving by using tan theta, which is giving 4.157, which is nearly to 4.16 meter. So the length of the bay under consideration is 4.15 meter or 4.16 meter, which is the actual span which you have to consider for the load application. Now that you got the span, you need to make sure that you get the area. So the area under this particular region is nothing but 4.16, or in other words 4.157 multiplied by the thickness of the wall. The thickness of the wall is 200 mm or 2.2 meter. When you're multiplying 4.157 into 200 mm, you will be having the cross-sectional area of the wall that will be taking that vertical load. If I just flip this below, ignore these points. These are not meant to be over here. This is just a one directional pair combination. So I'll just try to remove these. or not. I'll but just please ignore the bottom two projections. We're just considering this projectional part. So this 4.16 meter from this point to this point, I'll try to shade in a different color. So this red shaded portion is nothing but 4.16 into 0.2 meter, or in other words, it is 4.157 mm into 200 mm is the area of this red shaded portion. Now we are trying to include this projection of the pier as well, which is nothing but 200 and 400. So we're multiplying 400 into 200 and we're adding that to this red area as well. So 400 into 200, that will give us 80,000, and that will be 80,000 mm square. Now that will be added to the total wall area as well. So we have 415 mm into 200 mm plus 400 mm into 200 mm, that is the pier projection area and the wall area. We get 91.14 into 10 power 4 mm square. That is the total area of this red shaded portion, and it is this red shaded portion the entire load is acting upon. This is the area on which the load is acting upon. Moving on, now that we calculated the area on which the load is being acted, we need to calculate the total amount of load that is actually happening. In order to do that, we're just simply multiplying first the self weight. In order to get the self weight, we are multiplying volume to its unit weight or density. So the volume over here is 3.6 meter, which is the height, multiplied by that cross sectional area. We get the volume of this particular span. So 3.6 into 91.14 into 10 power 4, that will give us the volume of that particular section, volume of that particular area, part, and we are multiplying that with 20, which is nothing but the unit weight of brick, or we can multiply it with density as well. So either way, we get 65.6 kilonewtons, which is the total load that is happening on this red shaded portion. That is the self weight, that is purely self weight. Now we need to calculate the local roof loading. Now roof loading, we have it in 7 kilonewton per meter, 7 kilonewton per meter, which is a UDL. So we are having it over a span of 4.15 meters. So we are multiplying 4.15 meter into 7. That will give us 29.1 kilonewtons, which is the uniformly distributed load happening on this span or this shaded area. Next, we have a concentrated load of 30 kilonewtons. Again, we are going to include the concentrated load here as well because it is being distributed all the way to the bottom. So the concentrated load is 30 kilonewtons, that is 124 kilonewtons, which is the overall summation of all the loads that are happening. That is 124 kilonewtons. So again, a simple formula, stress developed is load by area, 124 kilonewtons by 91.14 into 10 power 4. That gives us 0.14 Newton per mm square. That is the amount of stress that is developed in this shaded region by the virtue of all the loads, be it concentrated load, self weight, roof load, whatever loads that are happening on this particular example. Next, moving on, effective thickness. So the next step, in order to calculate the effective thickness, we need to know these specifications, the cross-sectional dimensions. Please be sure not to confuse with TP, TW, SP, and SP and WP. TP is nothing but the thickness of the pier, which is this one, 400 mm. TW is nothing but the thickness of the wall, which is 200 mm. WP is nothing but the width of the pier, which is 400 mm, this one. And SP is nothing but the span of the pier. Again, it is 4.5 meter. Not to confuse with 4.16, it is 4.5. When they say span of the pier, it means that the center to center distance between the piers that are existing in that particular building, the 4.5 meter. So please make sure not to confuse with 4.16 and 4.5 meter. Moving on, the idea is to calculate the effective thickness is to get the stiffness coefficient because of the existence of piers, or if there are any buttresses in any other application, we need to calculate, we need to take into the consideration of the stiffness coefficient over here. It's table 6 from page 14 IS 1905, table 6, which is over here. Yes, stiffness coefficient for walls stiffened by piers, buttresses, and cross walls. So let's just quickly see what is TP by TW. Our TP by TW is 2, 400 by 200, that is 2. So we are going to see for column number 4, which is over here. Next, SP by SW, what is 4.5 meter by 0.4 meter, that is 11.25. SP by SW, we have somewhere in between 10 and 15, 11.25, it is between 10 and 15, so we need to interpolate that. So on linear interpolation for column 4, we get a stiffness coefficient of 1.175. 1.175 is somewhere in between these two. That is the stiffness coefficient we get for that particular combination. Now that stiffness coefficient is multiplied with the actual thickness of the wall. The thickness of the wall is 200 mm. The thickness of the wall is 200 mm. Now we are multiplying that with the thickness of the wall. Now we get 235 mm as the effective thickness. Now once we get effective thickness, the next thing is effective height. It's quite straightforward. Everything is rigid on top and bottom. It's fully restrained on top and bottom. So we are just simply going to table 4 and we are looking for a fully restrained top and bottom condition. Fully restrained top and bottom condition in table 4, that is the first one over here, which is 0.75 times its actual height. So 0.75 into 3.6 or 3600 mm, which gives us 2.7 meter or 2700 mm. Next, the slenderness ratio, effective height by effective thickness, which is nothing but 2700 mm by effective thickness, which is 235. We got that in the previous step. By doing so, we get a slenderness ratio of 11.5. Now once we get the slenderness ratio, we need to calculate the permissible compressive stress. Now in order to calculate the permissible compressive stress, we need to go to table 9, which gives us the stress reduction factor. Going to table 9, the stress reduction factor for slenderness ratio and eccentricity. For this particular problem, we are not having any eccentricity. We didn't mention it. It is not mentioned in the question anywhere about eccentricity. So we're going to take eccentricity as 0 over here, which is there in the first column, 0 eccentricity. Now for 0 eccentricity and a slenderness ratio of 11.5, which is somewhere in between 10 and 12, we get a stress reduction factor of 0.85. That is the stress reduction factor, which is somewhere in between this. On interpolating, we get 0.85. Now that should be noted, it's a small correction, 0.85, not to consider 0.73, which is written. It is 0.85. Now for a brick masonry of 7.5 Newton per mm crushing strength and a type for an M1 type mortar, the basic compressive stress is 0.74 meter. Now that 0.74 is nothing but the value which you get from your table 8, 0.74, 7.5 crushing strength, M1 mortar. So 0.74 is the basic compressive stress. Now we are going to multiply 0.74 to the Ks, or the stress reduction factor, to get the permissible compressive stress. 0.85 multiplied by 0.74, that will give us 0.74 multiplied by 0.85, that will give us 0.629 or 0.62, which is the permissible compressive stress. Please ignore 0.58 over here. That is wrong because they have considered 0.78 as the stress reduction factor. So please ignore the written values of Ks. Please follow the annotated values which are given in red over here. So we get the permissible compressive stress as 0.629. That is the permissible compressive stress, and that is actually greater than 0.14, which you have got over here. The total actual load, that is 124 kilonewtons, that is happening by the virtue of self weight, concentrated load, and the roof load. to the area which is shaded in red. If you see this, the entire load that is happening on this red area is 124 kilonewtons, and the stress is developed is 0.14 newton per mm square. That is the actual on-site load application or stress developed in that particular shaded area. Now, the permissible stress that can be allowed in that particular area is 0.62, and that is well over 0.14, or 0.14 is well below 0.62, which is a safe thing, and we can make sure, we can consider that everything is under a safe range of application in terms of load. So this is how you solve when it comes to concentrated loads. It's similar to that of your UDLs, but only thing is that for concentrated, you need to make sure that you find the span of load application through that trigonometrical approach where the load is dispersed at 30-degree dispersion. So with this, I'll conclude this session. You can feel free to reach me out on my email or number regarding this particular session. So with this, thank you. Bye-bye.